Okay, guys, these are some mixed practice integrals from a different book, and primarily these are by parts, but some of them don't require by parts. Some of them might be just a simple U sub. Okay. Now, in this book, at this point, trig sub had not been taught, and neither had partial fractions, so that'll be our primary focus. Okay, is going to be by parts, but then also we might just be able to do a U sub. Okay, so here's one, the integral of x e to power negative 2x dx. Okay, so from here we can just try to do by parts because it's a product of two different functions. One of is algebraic, one is a transcendental function, an exponential function specifically. So let's let u equal x. That will imply that du is equal to dx. dv would equal e to power negative 2x. So that means you're going to have to figure out what v is. Now, I believe this should be negative 1/2 e to power negative 2x. How do we know that? Okay, you could come over here and you could just try to integrate what is e to power negative 2x dx. You're going to need to use a substitution, so suppose t is equal to negative 2x, that would mean that dt is going to be negative 2 dx. So you need a negative 2 here, and then a negative 1/2 here, and then ultimately it becomes negative 1/2 times the integral of e to power t dt. And then, you know, it's just e to power t plus a constant, but you have this negative 1/2 there, and then the t was negative 2x. And so that's ultimately going to be the integral, and in the situation we're in, we don't need the plus c. Okay, if you just memorize, I think I mentioned this before, but if you just memorize that the integral of e to power a, or you could call it ax, for example, you could say ax dx. If you just memorize that this is going to be 1 over a times e to power ax plus a constant, then that's probably going to make your life a little bit easier. And that's, of course, where a is a constant, okay? So just keep that in mind. Now, okay, also keep in mind, you know, that suppose, let me write this down again, e to power ax dx. If, I told you it's 1 over a e to power ax plus a constant. If a is something like 1/2, then the same rule applies. So that would mean that this would be e to power 1/2 x dx. That would mean that this is going to be 1 over 2 e to power 1/2 x plus c, and then 1 divided by 2 is 2. Okay, so make sure you kind of keep that in mind, and that's the idea. Okay, so just sort of keep that kind of stuff in mind. It's useful to keep that in mind. Okay, so then from here we have that that the integral of x e to power negative 2x dx, it's going to equal u times v. So x times negative 1/2 e to power negative 2x minus the integral of v du. And so no problem. So now this is x times negative 1/2 excuse me, times e to power negative 2x plus, and this is going to be a minus 1/4. Why? Because the a here is negative 2. Remember, we just had this conversation over here. So, and that means it's going to be, there's a 1/2 there, but then you're also going to have a negative 1/2 in front. Negative 1/2 times 1/2 is negative 1/4, and then this becomes e to power 2x plus constant, and so that ends up being your answer. Okay, I'll call this number 1. Let's do another one. Okay, so how about this one? It's the integral of 2x divided by e to power x dx. Okay, and so problem like this one, you can try to do substitution. And so what I would do is I would first rewrite this as 2x times e to the power negative x dx. And then I would go on ahead and just sort of do what you did a second ago. Yeah. So, and then what I would do is you could pull the 2 out. And then you could let u equal x. That would imply that du is dx, but then dv is e to the power negative x. V is going to be negative e to the power negative x plus a constant, but you don't have to write it there. Okay. So then this is now 2 times, and then it's u times v minus the integral of v du. Okay, now why did I make this a plus sign? Because this had a negative, so this negative, which was here, I pulled it out, and that made that positive. So that's why I did that. Okay, so now this is going to become negative 2x e to the power negative x plus, and then I'm distributing this to 2 times, this is going to become a negative because it's a e to the power negative x, so negative 2 e to the power negative x plus a constant. Okay, how did I integrate this that quickly? Okay, I just go back to this conversation that we had over here at the very beginning of the lesson. If you memorize that the integral of e to the power ax dx is 1 over a e to the power ax plus a constant, your life's going to be a lot easier. And that's what I'm doing here. I just memorized, I just used that fact here. Okay. Alright. So that's great. Let's do another one. Okay, this is the integral of x cubed e to the power x dx. I would recommend the tabular method on one like this. So we have the sine, then we have u, and we have dv. Okay, so what we're going to do here is we're going to start off with a plus sign. You always start off with a plus sign when you're doing your tabular method. And let's start off with the thing that we're going to differentiate first, which is going to be the x cubed. And let's just continue to take derivatives here until we get 0. So 3x squared, 6x, 6, and then 0. Okay. And so for your signs, they're just going to alternate plus, minus, plus, minus, plus. And then over here, we're going to pick the thing that we're going to integrate, which is e to the power x, 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 e to the power x. Okay. And then just keep in mind that when you integrate this thing, you're going to get this sign, and then this times this. Then you're going to get plus or minus, in this case minus this times this, plus this times this, and then minus this times this. So that's going to be the process, and then you're done. So we're going to get x cubed e to the power x, and then minus 3x squared e to the power x, and then plus 6x e to the power x, and then minus 6 e to the power x. And then you could just put plus a constant, and then you're done. That's a lot faster than having to go through by parts like 3 times. Okay, I think you'd have to go through it 4 times, to tell you the truth. Well, three times you'd have to pick a u and a v, but you'd have to, yeah. Okay, let's do the next one. This is the integral of e to power 1 over t over t squared dt. Okay, so for this, I would consider rewriting this, and well, let me see here. Oh, I think for this we could just do a u sub. I think. Let's try it. Let's let u equal 1 over t, and that's the same thing as t to the power negative 1, but that would imply that du is going to be the derivative. So negative t to the power negative 2 dt. Okay, and so, but that's the same thing as negative 1 over t squared dt. But if we look here, then this is the integral of e to power 1 over t, and remember that this is going to become u, and then that's going to be divided by 1, and then this is multiplied by 1 over t squared dt. Now if I put a negative here and then a negative there, then now this part becomes du. And so now this whole integral becomes negative the integral of e to power u du. And now this is an easy integral. So this is just going to be negative e to power u plus a constant. And then what was the u? It was 1 over t. So this is going to be negative e to power 1 over t plus a constant, and we're done. Okay, how was I able to tell that you could just do a u sub on that? Okay, remember with the u sub, what you're looking for is you're looking for something that's inside of another function. So one function inside of another. And so the function that's inside of another one, the innermost function, we would pick for our u. And then do you see the derivative of that inner function multiplied? So in other words, I knew, well, if I differentiate this, then I know I'm going to get like a 1 over t squared something. I think it plus minus something, and it's probably minus, and it turns out, yeah, it was minus. So it's like, but I know that I'm going to get the t squared business in the denominator, and that's what I have here. It's t squared in the denominator. So that's what I tried. So that's a good thing to keep in mind, okay? That's ultimately what I got. Let me make it a little bit bigger. I got the integral of e to power 1 over t all divided by t squared dt, that whole thing was equal to negative e to power 1 over t, excuse me, plus c. Alright, let's do another one. Okay. How about this one, number 15, or number 5, I said. I'm doing, yeah, because that was number 4, this is number 5. Okay, so this is the integral of x squared e to power x cubed dx. Okay, again, something as an inner function, and then its derivative is 3x squared, and you've got the x squared. So that means that we're going to just be able to do u sub, no problem. So what we're going to do is we're going to let u equal x cubed. That would mean that du is 3x squared dx. Okay, so now we need to put a 3 here and then a 1/3 there, and then this whole thing becomes 1/3 times the integral of e to power u du. Okay, and so now this is 1/3 and then e to power u plus a constant, but what was u? It was x cubed, so this is 1/3 e to power x cubed plus a constant, and we're done. Okay, let's look at number 6. Okay, how about this one? This is the integral of x to power 4 times the ln of x dx. Okay. Well, let's go ahead and try to do integration by parts on this one. because it's a product of two functions. Now, if you remember, like I kind of gave you guys that that rule of thumb. A lot of times you don't necessarily need it, but in this one, I want to pick my logarithmic to be my differential, or the thing that I want to take a derivative of. And the reason is because I know its derivative is 1 over x, which that means that this is going to get knocked down a little bit, and then also it should just end up becoming that second integral ought to just be like a power rule, simple, straightforward one. So we're going to let u equal the ln of x, but that implies that du is 1 over x dx. Now dv would be then x to the power 4, and that means that v is going to be x to the power 5 over 5. Okay, so let's try this here. This integral of x to the power 4 times the ln of x dx turns out is equal to u times v. So u times v, so that's going to be 1/5 times the ln of x times x to the power 5. Generally, I'll probably do it this way. 1/5 x to the power 5 times the ln of x minus the integral of v, which is this, du, which is that. Oh no, which is that. So I'm going to have this 1/5 x to the power 5 multiplied by 1 over x dx. And so now, when you multiply those, this becomes the integral of just x to the power 4 dx. Okay. Well, so now it's just a power rule on this last integral, and it's easy. So this is going to be 1 over 5 x to the power 5 times the ln of x minus 1/5 times x to the power 5 over 5 plus a constant. And so ultimately, you're going to get, this is 1/5 x to the power 5 times the ln of x minus 1/25 x to the power 5 plus a constant. Also, if you wanted to get real fancy pants, what you could do is you could pull out a 1/5, and you could pull out an x to the power 5, and what you would get is you get 1/5 x to the power 5 times, and you get the ln of x minus 1/5, and then plus a constant. Now, how you want to play the constant is, I'll put plus a constant like that inside there. It's fine. Well, let me see. I'll tell you what. And then I'll do plus a constant like that. Because otherwise, to be fair, what you'd really need to have done is you would need to rewrite this as like times x to the power -5 or something like that. So, like if you were going to put it inside. So let's just leave that alone. That's good enough. I'll accept this as well. Either one is okay. I'll accept either one. Okay. So let's see. That was number 6. Let's do number 17. Or number 7, I mean. So we have the integral of t times the ln of t plus 1 dt. Okay. Now in a problem, or in a problem like this one, so let's see here. I kind of feel a little bit uneasy the fact that this is a t plus 1 and this is a t. I don't like that. Not really. So it might just be one where we can just do by parts, but and probably we're gonna need to do by parts anyway. But I kind of want this to match this, or at least I'll say this. I would really prefer this to be just a single variable. So let's just try to do something here. Let's let I gotta pick another letter. So I don't really want to pick like U or V because I want to use those for by parts in a second, I'm sure. Oh, I know what I'll pick. X. Excuse me. So let's see here. Let's let x equal t plus 1. That means that dx is going to be dt. Okay. But that also means then that t would equal x minus 1. So now this is going to be the integral of x minus 1 times the ln of x dt. Okay. So now what we could do is we could split this actually by distributing. So we could rewrite this as the integral of x times the ln of x minus the ln of x. Oh, this is supposed to become a dx, by the way, dx. And then you could just split this into two integrals. So now we could rewrite this as the integral of x times the ln of x dx minus the integral of the ln of x dx. And then this one becomes 1 over x plus a constant. This one we're going to need to do by parts on. So, whoops. So let's do by parts. So let's see here. We're going to let u equal x. That would imply that du is dx. Then dv is equal to the ln of x. No. I'm sorry. Take it back. I want to integrate the ln. So I'm going to let u equal the ln of x. And then that means that du is going to be 1 over x. Remember, more often than not, the substitution we want to do is we want to pick the ln to differentiate. And then the dv is going to be x, so that means that v would be x squared over 2. Okay, so now this part is going to equal u times v. So the 1/2 and then x squared and then the ln of x. Yeah, and then minus the integral of v du. Okay, so now we've got this 1/2 x squared ln of x minus 1/2 the integral of, well, x squared divided by x is just x, and then minus this 1 over x plus a constant. And then for this is going to be 1/2 x squared times the ln of x minus 1/2, and then this is at x squared over 2 minus 1 over x plus a constant. So this is 1/2 x squared times the ln of x minus 1/4 times x squared minus 1 over x plus a constant, and that is it. Okay, now let's go back here. Did I need to do this substitution here? No, probably not, but that's what I did. So I felt like it. I don't know if it was exactly what was necessary, but it's what I felt like. Oh, as a matter of fact, we got to still back up one more time, because we've got everything in terms of x, but it's supposed to be t. So this is supposed to be, let me rewrite this. This is 1/2 t plus 1 all squared times the ln of t plus 1 minus 1/4 times t plus 1 all squared minus 1 over t plus 1 plus a constant. Okay, so that's the answer. So yeah, as far as like I was saying earlier, I mean, did I need to do this substitution? I mean, like I said, I'm not sure if you needed to do it or not. You could maybe do it another way without having to do that substitution, but I felt like doing the substitution because I didn't like the fact that this had a t plus 1 in it. I don't know, it's just instinct, feeling, gut feeling. I didn't like it, so I wanted to get rid of it. Could you have just went through by parts without changing that? I think so, probably. You know, it'd probably work out okay. I don't know. Excuse me. Without having tried it. But I think it probably could have worked. I mean, it's worth a shot. You know, you just try it and see. Okay? Let me know how it turns out. Alright, then here's number 8. Let's do number 8. Okay, this is a good one. The integral of 1 over x times the ln of x. Oh, wait, let me get back to this. 1 over x times the ln of x all cubed dx. Okay. this is actually just a u sub, and it ends up being real like wow, like it's kind of a real wow thing. Now, if you've seen this before, you're probably not going to be very wowed by it, and even if you haven't seen it before, you might not be wowed by it. I'm wowed by it. I think it's very interesting, but I have a low threshold of interesting. So let's see here. Let's let u equal the ln of x, and that would imply that du is 1 over x dx. So now, if you notice here, this integral is equal to, I'm going to rewrite this as 1 over the ln of x all cubed times 1 over x dx. And if you notice, this is this. So that means this is du. And that means that this part is u. So ultimately, what you're going to get is you're going to get this is equal to the integral of 1 over u cubed du. So you could rewrite this, in fact, as the integral of u to the power negative 3 du. So now that's going to be u to the power negative 2 over negative 2 plus a constant. And then u, remember, was the ln of x. So you could actually rewrite this before we do that as negative 1 over 2 u squared plus a constant. And then u was equal to the ln of x. So that means that this is the same thing as negative 1 over 2 times the ln of x all squared plus a constant. That's it. Okay, that was number 8. Let's do number 9. Let's see, we have the integral of the ln of x, and that's all squared, and then it's divided by x dx. Okay, this is going to be the same kind of deal. If we let u equal the ln of x, then du is 1 over x dx. And you can see here then that this is going to be the integral of u squared, and then there's the 1 over x dx, so that's du. And then you just get u cubed over 3 plus a constant. And then the u is the ln of x, so this becomes the ln of x all cubed over 3 plus a constant, and that's it. Okay, that's number 9. Okay, let's try number 10. Okay, on number 10 we have the integral of the ln of x all divided by x squared dx. Okay, so what you could do is you could rewrite this as the integral of x to the power negative 2 times the ln of x dx. Okay, I'm going to go ahead and opt to pick the ln of x to be my u. I don't know if that's the right thing to do, but I'm pretty sure it's going to be the right thing to do because its derivative is going to be 1 over x, and it'll combine with this, and then you're going to get the power rule. So I'm pretty sure it's the right thing to do. Alright, but let's try it. We're going to let u equal the ln of x. That would imply that du is going to be 1 over x dx. But then your dv then is going to be x to the power negative 2, and that means that v is going to be x to the power negative 1 over negative 1, you know, plus a constant, but you don't have to write plus a constant. Okay, so then this is going to be the integral of, oh no, I'm sorry, the integral is going to equal u times v, so negative 1 over the ln, I'm sorry, negative 1 over x, and then it's u times v, so that's the v, and then the u is the ln of x, so ln of x, I'll put the ln of x on the top. So it's the negative the ln of x over x, that's the u times v, minus the integral of v du, so v is already negative, so that makes this positive. It's x to the power negative 1, and then du, that's 1 over x dx. So if you notice, it's the same thing. So this is negative the ln of x over x plus, and then this is the integral of x to the power negative 2 dx. So what you could just do is you could rewrite this thing as x to the power negative 1 over negative 1 plus a constant, and then just say no problem, this is negative the ln of x over x minus 1 over x plus a constant. Okay, that's it. Okay. Well, that's cool. All right. Let's try another one. How about number 11? All right, these are getting a little bit harder. That's okay. Number 11. All right. This is the integral of, and then this is x times e to the power 2x all divided by 2x plus 1 all squared dx. Okay. All right. Make sure I copy this right. X e to the power 2x all divided by 2x plus 1 all squared dx. Okay. Yeah. All right. Well, okay. Again, my gut instinct is to I don't like this. I just don't like it. So my gut instinct is to try to make a replacement for that. The problem is if I can do that, I can already tell you. See, I can fix this up. That's okay. I can do that, and that's actually going to be kind of a neat little trick. I'll show you. But then, how about this? You're going to get a fraction. I think it's okay. I think it's okay. Look, I'm going to try to just do a u sub it first. Now, I think that we're probably going to end up needing to do by parts. Don't get me wrong. I think that's probably going to be necessary. But before we do by parts, I still want to kind of change this. Do you have to change it? Maybe not. But I feel like it. So I'm going to change it. I think it probably would need to be changed, to tell you the truth. So let's see here. I'm going to do a t substitution. I don't want to do u because I'm going to do u and dv for by parts. So let me call it t. So I'm going to let t equal this 2x plus 1 because that's bugging me. So then that would mean that dt would equal 2 dx. So now I can put a 2 here, I can put a 1/2 here, and then that means I've got a 1/2 times the integral of, and then this bottom is going to become this t squared. Right now it's 2x plus 1 all squared, but it's going to become t squared. And then this is a 2 dx, which that's going to become a dt. Now the question is, what about the rest of this stuff? How am I gonna do that? Because I've got an e to the power 2x, right? Well, I could multiply this by e, and then multiply this by 1 over e. You might see that and be like, what? Why are you doing that? Let me show you. E to the power 2x times e to the power 1 is the same thing as e to the power 2x plus 1. Oh, okay. And then that's the 2x plus 1. So then it's going to become e to the power t. So that's kind of that neat trick I was going to talk to you guys about. And again, you might not think it's neat, and that's fine. But I think it's neat. Okay, so let's see here. We have now e to the power 2x plus 1, and then we still have a 2 dx over here, and then that's all divided by 2x plus 1 all squared. But there was still a problem. There was still an x here, so I still need to put an x there. Okay, so that's being said, I'm going to have to put an x here, but I don't, I need to figure out what that's going to be in terms of t. So then I'm going to come back to here. So this is going to be t minus 1 is equal to 2x, but that means that x is going to equal t minus 1 all over 2. So then let me put that in. Okay, so now ultimately I'm ready to do my substitution. This is the integral of x becomes this whole mess of stuff, t minus 1 all over 2. T minus 1 all over 2, and then we have multiplied by e to the power t divided by t squared, and then dt. Alright, and so now let's kind of clean some of this up. I'd rather not deal with all of this, so so let's see how that's going to work. This half can come out, and so this can become 1 over 4e times the integral of, now it's just t minus 1 times e to the power t, all divided by t squared dt. Okay. Alright, so I handled the problem that was kind of bothering me. Yeah. Now what you could do, I'm just trying to think if that would matter. Let's see, t over t squared. So the t's cancel, so you're gonna, okay, e to the power t over t. Okay. Okay, I think what I'm going to do from here is I'm going to rewrite this. I'm gonna do this. I'm gonna multiply in the top, and this is gonna become t e to the power t minus e to the power t, and that's all divided by t squared dt. And now I'm gonna split it into two. So I have 1 over 4e times, and I'm gonna have the integral of t e to the power t over t squared dt, and then minus the integral of e to the power t over t squared dt. Okay, now in this one you can make a little bit of a cancellation, and so this is now 1 over 4e times the integral of, and you could call it e to the power t over t dt minus the integral of e to the power t over t squared dt. Okay. Now, I think we solved a problem pretty similar to this earlier. So what I'm going to choose to do is I'm going to pick my 1 over t to be the thing I want to integrate. It's not common, but I think that's going to work. So let's see. 1 over 4e. So for this first one over here, I've got u is equal to 1 over, no wait, I'm going to pick e to be, the thing I'm going to differentiate is e to the power t. I don't know if that's going to work. Let's try it. U is equal to e to the power t, and then du is going to be e to the power t dt. And then dv is going to be 1 over t. That means that v is going to be the ln of t. Okay. So then that means that now for this first one we have u times v. So we have e to the power t times the ln of t, u times v, minus the integral of v du that's the ln of t times e to the power t dt. See, I was kind of thinking in my head, oh, that's going to be a neat trick because I have an ln and an e, but that's not as neat as I thought it was going to be. It's rare that you want to pick the e to the power t or the exponential to be the thing that you're going to differentiate, and I don't think this is going to work out as slick as I thought it was going to. So, let's try to, yeah, let me try something else. Yeah, so let me try something else. Let me just try to do this. Well, let me think about this. I had done something like this earlier, hadn't I? I had something kind of like this. I thought maybe I didn't. No, I guess not. Okay. Okay. Well, I'm pretty sure this isn't gonna work. Like, at least not like this. Because I just don't see this getting any better. I mean, I might be wrong. Because, I mean, it's just that you would need to pick u to be the same thing, e to the power t, and then that means your du would be e to the power t dt, and then your dv would be the ln of t, and that means that v would be t times the ln of t minus t. And then u times v would be that, which is fine, minus the integral of v du. Yeah, it's gotten worse, man. Like, no. I don't think this is the way we're going to want to go at all. Okay, so like I said, I mean, I was kind of thinking, oh yeah, the ln and e, they're going to destroy each other. Like, there's going to be some neat little magic trick that's going to pop up, but it didn't. So, let's go back one step. And instead, let's try to do this. You could rewrite this as t to the power negative 1 e to the power t. And you could rewrite this as t to the power negative 2 e to the power t. And then what I could do is I could pick u to be the t to the power negative 1, and that means that du is going to be negative. What happened? That means du is going to be negative t to the power negative 2 dt, and that means that dv is going to be e to the power t, and that means that v is going to be e to the power t. Okay, so let's try that on that one. Over here, we're gonna, I think, have to do kind of the same deal. Let's see how this first one kind of turns out first. U times v minus the integral of v du. So there's the plus, and you're going to get t to the power negative t yeah, so okay, so this is plus, okay, so u times v minus the integral of v du, and so the minus from this came out and made this a positive, and then it's e to the power negative t dt. Yeah, I'm sorry, t to the power negative 2 e to the power t dt. And then here's what's interesting. This integral, if I just recopy that here, then this is now minus the integral of e to the power, yeah, I'm sorry, minus the integral of t to the power negative 2 e to the power t dt. Well, now this and this are just going to add together to get nothing. And we're done. That's weird. I've never heard of that happen before, ever. I'm very surprised right now. So this becomes e to the power t over t plus c. I can't believe that. And then t is 2x plus 1. So this whole thing becomes 1 over 4e times e to the power 2x plus 1 divided by 2x plus 1 plus a constant. And then this e could cancel out with that, and you're left with e to the power 2x all divided by 4 times 2x plus 1 all plus c. Well, that's very interesting. Yeah, I've never seen anything like that before ever happen. Ever. Never. That's interesting. Well, here's the only thing I can say. Maybe, you know, this substitution... Excuse me, sorry. Maybe this substitution was not necessary at all. I mean, it's not, you know, I mean, it maybe wasn't something that you had to do, but I kind of thought, well, like, I kind of want to do that. But, yeah, I guess not. I mean, the only other way you could have done this up front without doing that substitution, because it's 3 functions. It's a product of this one, and then it's divided by that one. So it's sort of like kind of tricky. You could do associativity, or you could use associativity, which is to say you're going to group two of them together. So let's see. How else could you have done this? So, I mean, this is the answer, I'm sure. I mean, you could check it by differentiating it. So the C is going to go away, and then you've got the quotient rule. So you've got the bottom times the derivative of the top, which is e to the power 2x times 2 minus the top times the derivative of the bottom, which is going to be 4 times, let's see, I'm going to differentiate the 2x plus 1 and I'm going to get 2. So bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then let's see, what could you pull out? You could pull out an e to the power 2x. You could pull out a 4. You can pull out a 2. So you can pull out an 8. You'd be left with the 2x plus 1 minus 1 all divided by, this becomes then 16, and then 2x plus 1 all squared, and then that adds together to get nothing, and you're left with now e to the power 2x times 2x all divided by, and actually let me see, this 2 and this 8, this 2 and this 8 make 16. So I'm going to erase that 2, and I'm just going to call this x, and the 16 is gone, and you get 2x plus 1 all squared. And I think that's what we had. What was that? X e to the power 2x all over 2x plus 1 all squared. So that means we checked it, we differentiated it, we got the same thing. So that means it's good. That's definitely the right answer. Okay, so that's fine. I'm really curious about this problem because I have not seen a problem before where this sort of thing happens, where when you split it up you get two integrals and then they both kind of destroy each other. I've not seen that. At least not. Maybe I've seen that before in a different context. But just the same, it's very surprising. So was there another way to solve this problem? Now I'm curious. So let's see. You could have done this. (2x plus 1 all squared dx). Okay, could you have just done it this way? Could you have just said, alright, I'm going to let u equal my x over 2x plus 1 all squared, and that would imply that du is going to be, this is going to be gross, bottom times the derivative of the top minus the top times the derivative of the bottom, which is 4 times the 2x plus 1 all to the power 1, and then times the derivative of the inside, which is 2x, and that's all divided by 2x plus 1 all squared. Oh, and then squared. So then, that's pretty gross. Let's see. We get a 2x plus 1 all squared minus, okay, there's an x, there's an x, there's a 4, so this is 8x squared times 2x plus 1, and then it's all divided by 2x plus 1 all to the power 4, and then you can pull out a 2x plus 1, and you'd be left with 2x plus 1 minus 8x squared, and then that's all divided by 2x plus 1 all to the power 4, and then that cancels with one of those, and you still got all this mess of stuff. Yeah, you don't want to pick that for your u. No. So what could we have done instead if you wanted to just go for by parts? Well, we could have, how are we going to integrate that thing? Well, let's just try this. Let me see here. So let's see. If we let u equal, not that, because that's going to be horrible. If we let u be e to the power 2x, so that means that du is going to be 1/2 e to the power 2x. That means the dv would be this x over 2x plus 1 all squared dx. And that means what about v? Well, you'd need to go through here and do a substitution. So you let t 2x plus 1 would equal t. That means the dt is 2 dx. Yeah, I mean, this is getting pretty not good. I think the way I did it is going to be the only real viable way. Maybe, you know, like I say that, I mean, I'm kind of giving up on the substitution because I can sort of just in my mind imagine people trying to watch this thing and they're like, I don't care, you got the answer, whatever. So that's fine. But I mean, I think there's probably something you could try to force. You could try to force to do a substitution like this in another way. I think you could probably make it work. But I don't know. I think this worked though. That's amazing. I've not seen a problem like that before. That's at least not that I can remember. I mean, you know, maybe I have, but you know, I don't really remember it. All right, number 12. Okay, number 12. Okay, how about this one? I wanted to work this one the other day, and then I didn't have time. So let's do this one. X cubed e to the power x squared, all divided by x squared plus 1 all squared dx. This one's kind of similar, a little bit. If I say that, what? Yeah, I think so. Yeah. But this one's got an extra by parts in it. I think that was the deal. Okay, so here's how this one works. I think this is how this one's gonna work. Because I worked this one out, I think, the day for myself, and I was gonna show it in a video, and then I didn't have time. So let's see here. Let's let u equal x squared plus 1. Let's try that. Okay, let's just try that. And then that means that, or let me call it t. Oh, well, and I wasn't done. Oh, yeah, I was on this one because I did substitute back, right? I went all the way back to the original variable x. Okay, yeah, so that was finished. Okay. All right, so let's let t equal x squared plus 1. That implies that dt is equal to 2x dx. And then there's okay, so how to do this? So now what I can do is I can rewrite this as x squared times e to the power x squared times x dx, and this is like this. Okay, so I need to put a 2 here and then a 1/2 here, and then this would become my dt. This would become my t, and then like the that this implies that t minus 1 would be x squared. So that means that, and you got choices. You could either put a plus 1 here by multiplying this by e to the power 1 and then this by 1 over e, like I had said earlier. Or if you do the substitution, then that's going to become e to the power t minus 1, and you could say that that's e to the power t divided by e, and then you get the 1 over e that will come out of the integral, so you still get this 1 over e on the outside. So in either way, you could get it, and that's fine. But let's write it this way, and then the integral of, and then let's see what's going to happen here. So I believe that this x squared is going to become a t minus 1, and then this becomes e to the power, because this is e to the power x squared plus 1. This is e to the power x squared plus 1, so that's just e to the power t. and then this is a dt now, and that's all divided by t squared. Yeah. And so was this the same one though? T minus 1 times e to the power t all over t squared. I thought I worked this one out a different way. T minus 1 times e to the power t all over t squared. Okay, well then from there you could, I guess, just work it out the same way that I had worked it the other one out above, because this is the same substitution. I mean, like, after you substitute it, you just get the same thing. T minus 1 times e to the power t all over t squared. But I was pretty sure that I had worked this out another way. And I thought that, what had I done? Maybe this is it, I guess. I don't think so. I thought I did something else. T squared, x squared plus 1. Okay, well I guess that's it. It's the same thing, and then you could just go this. So like I'll leave this for you. So then you just integrate that. You just do the same thing I did up there. I mean, I'm pulling these out of another book, and they had done. I mean, they're adjacent problems, so it makes sense that they're similar. But I could have sworn that there was another way I had done this problem where I did by parts. You know, like a different way. And but I can't remember it now off the top of my head. I thought I guess that's it. I have to reflect on this. Okay, so that's it. That's kind of some U-sub problems. Let me do. I kind of wanted to do another one. Let me do a definite integral one. How about that? Okay. I'll leave this for you. I mean, this problem's not done, but you can finish it. Let me do another one here. This is a definite integral. One more problem. This is an arc sine. This is a definite integral. So let's evaluate the integral from 0 to 1. I guess this is number 12, so this will be lucky number 13. That'll be the last one for this video, okay? And this is going to be the integral from 0 to 1 of the arc sine of x dx. Okay? So we're going to do this with by parts. And what we're going to do is we're going to let u equal the arc sine. Okay, and then remember, we know the derivative for this one. This is going to be 1 over the square root of 1 minus x squared dx. And then our dv is going to be just dx. And then that means that v is going to be x. And so now what we can do is we can rewrite this, the integral from 0 to 1 of the arc sine of x dx, we can rewrite that as u times v. So x times the arc sine of x evaluated from 0 to 1 minus the integral of from 0 to 1 of v du. Okay. And then this one's going to be a simple u sub. I'll pick my u to be my bottom. Okay, so now I can do that. I can just do just a simple kind of, just a normal change of variable like a u sub. So, or I'll use t because I don't want to use u because I just used u, so I don't want that to be confusing. So then this is going to be t is equal to 1 minus x squared, but then that means that dt would equal negative 2x dx. So I need to put a negative 2 here, and then a positive 1/2 outside. And then that means that now, okay, in the meantime, let's try to evaluate this thing. So we're going to have 1 times the arc sine of 1 minus 0 times the arc sine of 0. So think about this. The arc sine, that's like saying this. If you know that the sine of theta is equal to 0, then that's like saying that the arc sine of 0 is equal to the theta. Okay, and so if you kind of want to say, all right, well, the sine of what is 0? Well, there's a lot of things, but inside the normal, considering the domain issues and the range issues with the inverse trigonometric functions, the sine of 0 is 0. So that means the arc sine of 0 is going to be 0. So this is going to be 0 times 0 minus, okay, let's play the same game with 1. Okay, if the sine of theta is equal to 1, then that's saying the exact same thing as the arc sine of 1 is equal to theta. So what is the theta value where that happens? Well, where's the sine equal to 1? You have pi over 2. Pi over 2 is definitely a value where the arc sine is equal to 1. Or, I'm sorry, the sine is equal to 1. So that means that the arc sine of 1 would be pi over 2, right? So this is going to be 1 times pi over 2. Okay, so we've got that. I need to get this out of the way because it's kind of in the way. Okay, so we've evaluated that. We figured that out. Alright, so then then I have plus, and then I have 1/2 times the integral from 0 to 1 of, and now I can change this. This is now 1 over the square root of t dt. And then how about this? Since I changed my integral, how about I change my limits of integration? So instead of 0 to 1, let's see. If x was equal to 0 with this substitution in mind, then that would imply that t would equal 1 minus 0 squared, which means that t is going to equal 1. So I'm going to make this limit of integration 1. And now I say, okay, well, if x is equal to 1, then that would imply that t would equal 1 minus 1 squared, which that's going to be 0. So that means t is equal to 0. So that means you're going to go from 1 to 0. Now if you're going from 1 to 0, that's kind of weird. That means you're sort of like going backwards. So remember, there's a trick in Cal 1. It says if you make this a difference, then that means you can change these limits of integration, and we're going to go from 0 to 1 again. And now you don't have to go back to x world. Okay, you can just stay in the t land. So this is going to be pi over 2, basically, is what we found. That's what this whole thing was equal to pi over 2, and then minus 1/2, and then this is the same thing as t to power, the integral from 0 to 1 of t to power negative 1/2 dt. And so this is going to be pi over 2 minus 1/2 times, you have t to power 1/2 over 1/2, and you're going to evaluate it from 0 to 1. The 2's will cancel, the 2 and the 1/2, and so then we have pi over 2 minus, and then you've got we've got the square root of 1 minus the square root of 0. So this whole thing is just pi over 2 minus 1, and that's our final answer. If you plug this in a calculator, it's approximately like 0.571. I had that worked out in advance. So that's the idea. So, but this is a final answer. Okay.